All right, so we're going to start today with a little overview of mass spec. I sent the mass spec video actually before we start the handout. We just do this. We go somewhere else. And then we'll look. I have a actually PowerPoint that out. I'm gonna share first. We'll walk through that and then we'll look at these mass spec problems. Mass spec is not as difficult to understand as NMR. It's not cake, but it's not a. All right, let me go. Let's see. Yeah, right here. So before we start working through this mass spec part of the handout, I want to talk briefly about like the technique and what it does. So these are some of the mass spec instruments. The instrument we have is similar to this one right here. We have a what is it? It's a LCMS or liquid chromatography mass a spectrometer. And it is a time of flight mass spectrometer. You can see, yeah, not on this one, but there's on a time of flight. What it is, it measures like the the velocity of the particles as they drop. So they go into this tube, the fragments do, and as they fall, the time of flight is measured. So we'll talk about that shortly. But these are some of your more traditional instruments. This is a portable mass spec. You've probably seen this in the airport. I don't know if I mentioned that before, because I've given this lecture more than once to more than one class. But the portable mass spec is after 9/11 when everything was going crazy and the TSA would swab your bag and take that piece of fabric and put it into this instrument. That was a type of mass spectrometry. So, and then the miniaturized mass specs actually do exist now. A mass spec on a chip. Um, I actually was at a conference when they were discussing miniaturizing mass spec. It wasn't, it was just an idea at the time, but now miniaturized mass specs actually do exist. So what do we use mass spec for? So we use it to identify unknowns, to quantify known compounds, to detect explosives. Talked about that a second ago with the airline detection. Crime scene investigation. And I say this all the time, like when you watch CSI or you watch NCIS or any of those types of shows like that, or what's the one on what's the channel? ID, like Investigation Discovery, all those true crime shows, and they show somebody in a lab, injecting something into an instrument. More than likely, that instrument is a mass spectrometer. So um, heavily used for crime scene investigation because every chemical compound has a specific molecular weight, which is what mass spec looks at. It looks at the molecular weight of a compound. So you can also detect like contaminants or toxins. And we actually have a project coming up, preservation project, where we're going to use mass spec to determine the chemical composition of the bricks that were used to build the university, as well as the bricks that were used in the Armstrong School, which is out near Bullitt County. It's the last um, standing rural school like in the area. Uh, so we're going to use this technique to actually test the paint and the bricks just to confirm that the same bricks that were used to build a university are the same bricks that were used in part of the construction of the school. So this is what the setup is. And I know if you watch the video, this part is kind of redundant, but you have your sample, you expose it to an ion source. In most cases, that ion source is an electron beam. And then that ion source is going to fragment your molecule, right? It will break it up into pieces. That's the best way to describe it. And when it does that, those pieces are going to have a specific molecular weight. So when it breaks those fragments into pieces, what happens in that particular case is the mass analyzer picks up those fragments and picks up their molecular weights. And then that information goes into a detector, and then the detector spits it out for you to analyze the data. And the good thing about like a lot of these mass spectrometers now is that they're huge databases, because you're talking about decades of research. So you have huge databases of compounds where you can use to match up your spectrum with some other spectrum, right? So that's a plus. So the way this works, you've seen this already. I'm just reviewing before we start working on the problems. So if you have like methane, for instance, methane is going to get pummeled with the electron beam, and eventually an electron is going to be forced out, right? And so when that electron is forced out, you get what's called here a radical cation, right? It's the radical cation that gets fragmented or broken up into pieces. So in this case, as I continue to pound on this molecule with the electron beam, right, I'm simulating that molecule basically exploding. It's not really exploding, but it's breaking. The bonds are being broken, and then you end up with fragments, right? So one of the fragments was a CH3, the other one is a H. And if you notice back here, this is a radical cation. So when the fragmentation happens, one of the fragments ends up becoming a radical, and the other ends up becoming the cation. All right, that's really important, and that's normally based on how stable one fragment is as either a cation or a radical. So if it's more stable as a cation, then that's the fragment that'll be positively charged. And if it's more stable as a radical, then that fragment will become the radical, right? So in a nutshell, how this works is you bombard your sample with an electron beam, you eject an electron, the sample becomes a radical cation. That radical cation is continually bombarded and gets broken up into fragments, and it's the fragments that get analyzed in a mass detector, all right? So this is an example mass spectrum, and you have some peaks in here that are really important. So you have what's called a base peak, which is normally the most intense peak in the spectrum, and it usually corresponds to your most stable fragment. Then you have your parent peak, which is the actual molecular weight of your compound. So if your compound has a molecular weight of 100, then the parent peak is going to be 100. If it has a molecular weight of 50, the parent peak is going to be 50. And then you have also within the spectrum what's called the M+1 peak, mass plus one. So if the parent peak is here at 46, then the M+1 or the isotope peak, notice it's much smaller than the parent peak. That's going to show up at 47. Right. So those are like the major features of a mass spectrum. You have your base peak, your parent peak, and then your M+1 peak. And then you should write this down somewhere. If you have a halogen present, then you can also see what's called the M+2 peak. All right, so that's the M+1 is an isotope peak, right? So that's your carbon 13 isotope of whatever molecule you're looking at. So that's going to increase the molecular weight by 1 atomic mass unit or 1 AMU. All right,
I have a question.
go ahead.
So you said the N+1 peak, where is that?
It's right here. So the parent is 46.
Mm-hmm.
So that the mass, that's the mass. So the mass +1 of M+1 is 47.
Okay.
Mhm. And then on the axes, the y-axis is relative abundance. X-axis is mass over charge, right? But the charge is normally +1, so it's really just corresponding to the mass. So you have here the mass, it starts at 10 and the spectrum goes to 50. So there's nothing heavier than 46 grams per mole in this spectrum, right? So we can actually use this spectrum. I wish I could. What can I do? What can I do? Let me. Yeah. So we're going to actually use this spectrum to figure out which of these compounds this spectrum corresponds to. So let me do something real quick. Let me take a screenshot of this slide and send it to myself. And then we're going to use this. We're going to actually use this to work through this example. So let me do that right quick. I should have done this already. But let me pause the recording. That dead space. Okay. So yeah, so now we have the spectrum here. So we got 5 compounds that we're going to work through, and we're going to use this spectrum to figure out which compound is here. So we can see what a base peak is. It's at 31. We can see the parent peak at 46, the M+1 peak at 47. We'll answer that last question shortly. So we got 5 compounds: formic acid, which is here. Um, 1-propanol, which is here. Too many carbons. Formic acid, 1-propanol, ethanol, and then methanol, and isopropanol. All right. So those are our 5 compounds. So I need somebody to look up the molecular weight of formic acid, 1-propanol, ethanol, and methanol.
Formic acid is 46.03.
Molecular weight of 46.03 grams per mole. Good. What about isopropanol? Anybody got that one? Or 1-propanol? Those are isomers of each other, so they're probably going to have that. Well, not probably. They should have the same molecular weight.
60.09.
So 60.09 grams per mole for those two. All right. What about methanol?
Ethanol is 46.07. Oh, wait, that's not yet. ethanol.
Okay. All right. And then methanol is 32, is that right?
Yeah, 32.04.
Okay. So now let's look back at our spectrum. I should make that. I'll make it bigger. Actually, but let me move these down and then I can. All right. So if we look at this spectrum, based on this spectrum, what's the heaviest compound that should be present here? Look at the range and tell me what's the heaviest thing that should be present. Not out of what we're looking at, but just period. What's the highest molecular weight that we can expect to see based on this range?
50.
50, right? Very good. So 50, anything that's 50 grams per mole or less, it would show up here, right? So with the range being what it is, which of these compounds can we rule out right away based on the range of the spectrum?
Is it the isopropyl?
Yeah, and 1-propanol, right? Because they have a mass of 60 grams per mole, and there's no peak in this spectrum that shows up at 60 grams per mole. The maximum mass that this spectrum is going to represent is 50 grams per mole. Are y'all following that? So we can rule those two out. Is that right? Any questions about that? Right, if there was a compound that had a mass of 60 grams per mole in this spectrum, then the spectrum would have to go out at least to 61 because you would have the mass, which is 60, plus the mass plus 1, which would be 61. And that's not present here. All right, yes, no, maybe.
Yes.
All right, what else can we rule out? What if this was a spectrum for methanol? Where should that x-axis, how far out should the x-axis go if it was methanol?
Would it be 32? Are we including methanol?
No, what I'm saying is if this was just a spectrum for methanol, what would the range be on the x-axis? You're right, you said it. You said
Yeah,
30.
at least at the 30. Yeah.
Yeah. And there should be nothing past that, right? If it was
Right.
methanol. Right. But you see peaks down at 45, 46, and 47. So we can rule out methanol because the range on the x-axis, the range of masses that's detected is greater than what the molecular weight of methanol is. Does that make sense?
Yes.
All right.
No, can you explain it one more time? You lost me.
So if the spectrum was only methanol, right? Because that's what this is. This spectrum is one of these compounds. If it was methanol, the masses that are detected will stop at 32.
Okay, got it.
Shouldn't be anything heavier than 32 grams per mole in there other than the M+1 peak, which would be 33.
Okay. So
Right.
it's between formic acid and ethanol. then.
Yes. So now we need to look at those two compounds and we're going to figure out which one this spectrum corresponds to. Move this over here. Move that over here. All right. So it's going to be one of these two compounds, either going to be formic acid or ethanol. So now what we need to think about is the fragmentation, how this thing fragments. So we're going to start with formic acid. All right. So if we look at the spectrum, let's look at the peaks that are showing up. We have a peak at 15. We have a peak at, well, we have other peaks here, but I'm looking at the major peaks that are showing up: 15, 29, 31, 45, 46, and 47. All right. So each one of these peaks represents a fragment or some way that that molecule can be brought, something, some piece of that molecule that is present when it's broken up, right? So each peak is a fragment. Let me write that in here. So each peak is a fragment of the original molecule. All right, so what I'm saying is when we start breaking this thing apart and breaking bonds, we need to be able to break off pieces that match up with the fragments that are in the spectrum. Are y'all following that? Anybody not understand that or not following that?
No, I got it.
All right. So the fragments have to match. So let's look at here. I'm gonna take this formic acid. I'm gonna redraw it. So here, right? So I could fragment this a few ways, right? But let me show you. So I'm gonna break this off, right? So the OH group by itself is 17 grams per mole, right? And then if the total mass is 46, then the other fragment has to add up to 46. So the other fragment has to be 29 grams per mole. You following? So that would give me these two pieces, OH and this, and I'm going to make this the cation, and I'll make this the radical. Right? Because again, when this thing starts breaking apart, it's the radical cation that's breaking up. All right, questions about that? So this is 17.
So we can choose which one is the radical or which one's the cation, or there's okay.
Yeah, you have to choose, but one has to be one and one has to be the other. So normally what I suggest is putting a radical or putting a cation on an atom that's where it can be stabilized. So that if I put that cation here on carbon, then oxygen can stabilize it by resonance. Right?
Right.
Mm-hmm. So that's 17, that's 29. Everybody okay with that?
Yes.
All right. So we can see that in here. That's a peak at 29. You could make the case for this peak being at 17, right? You can make the case for that. We know we have a peak at 29, but we also have to account for the other peaks. We got to account for 15, 31, and obviously 46 is accounted for because that's the molecular weight of formic acid. But we got to account for those through fragmentation, right? So let's take this formic acid. I'm gonna just copy it, and we're gonna cleave it on the other side. Because that's exactly what's happening in this instrument, in the mass spectrometer. You're banging on this thing with an electron beam, and it's just ripping it apart by breaking bonds, right? So then I can do that. Everybody agree with that?
Yes.
I can break that bond, and I can have this. I'll make this my radical. I'll make this my cation. Right, and then this is going to be 45, and this will be 1. Now, I mean, I have a peak at 45, we can account for that. But how do we account for the peaks at 31 and at 15? Is there any way we can fragment formic acid that'll give us those pieces? In other words, is there anything on formic acid that I can subtract from it and get and subtract away 15 grams per mole of that molecular weight to get a fragment at 15?
Oxygen.
Oxygen is 16,
Mhm.
right? And it's very difficult to cut a double bond.
Is the answer no?
The answer is no. There's nothing I can break off of that that's going to give me a fragment that shows up at 15. And also there's nothing I can break off of here that'll give me a fragment that's going to show up at 31. And that's really important because 31 is the base peak. That's your most intense, most abundant fragment, right? So if you can't do that, that means that this spectrum, there's no way this spectrum can correspond to that compound. Does that make sense?
Yes.
Yeah.
Yes.
So this can't, so formic acid cannot be but this spectrum can't represent formic acid. And I'll write it in down here why. So because there's no way to account for the fragments at 15 or 31. And this is really, the way I look at this is like putting a puzzle together. Right, so those the fragments at 15 and 31 grams per mole can't be accounted for with formic acid. So we can't use that spectrum. Are y'all following that? So let's look at ethanol. Ethanol, I need to do some finagling. I'll just put it on another page. Spectrum 2. All right. Let me get all of that. So ethanol is here. I'm just going to redraw it. All right, so it's CH3, CH2OH. So let's look at how we can fragment this thing. All right, we can fragment here. Actually, I'm going to draw the hydrogens in. I'll draw it in Lewis form. All right, so I can fragment here. Everybody agree with that?
Yes.
Yes.
And what would that give me if I broke it? If I broke that molecule or cut that molecule at that site?
Isn't that the OH? That's 17 grams per mole, right?
Mm-hmm. So we're gonna have OH. We'll make that
So
the radical.
29.07, something like that.
Something like that, right? So this is 17, and then the CH3, CH2. I'll make that the cation, and then so this will be what? 29. So far so good, yes?
Yes.
All right, now what if I cut it? I'm gonna change colors of the what if I cut it here? what fragments would that give me? Now, if I'm cutting there, I'm not doing both at the same time. You following? So what I break off from that particular fragmentation is going to be what, a CH3. Is that right? I'll make that my radical. And then what's left?
CH2OH.
OH, good. And I'll make that the cation. And this is what, 15. Is that right? Carbon is 12, hydrogen is 1. So that's 15 grams per mole. And then the other one, carbon
31.
is 31, isn't it?
Yep.
So now we can look back at the spectrum. What is the base peak based on this fragmentation pattern? Which one is the base peak? Which fragment?
CH2OH.
Good. The CH2OH. Are y'all following how that works? So
Yeah.
what we're doing is taking that molecule and chopping it in certain different places. And the fragments we get, if they match the spectrum, then we know that that's the correct spectrum for this molecule. All right. All right. Questions? Any questions? All right. What about 45? What can we do to get a fragment at 45? What do I need to subtract from the parent?
A
Can't you
hydrogen.
take out hydrogen?
I just cut a hydrogen off from somewhere, right? So let's
Okay.
just say we can cut it from here. Right? It can really come from anywhere, but we'll cut it from there. So that's going to be H, and we'll make that the radical. And then CH3CH, because that's where we took it from, OH, and we'll make that the cation. This is 1, and this is 45. So with that, we've kind of really accounted for all of our peaks. And these other little secondary peaks down here, normally those are fragments of fragments, right? So the fragment at 29, you can lose the hydrogen from that, or you could chop it in half, which would give you a peak at 15 and one at 14. So there are other fragmentation patterns that can happen, but for the most part, what we're looking at here, we're just looking at the major fragments, right? And we go ahead, Cornetta.
So is the base peak like the most stable peak?
Yes, most
Okay.
stable and most abundant.
Okay.
Mhm. And you can see that here. Some of them is not so clear cut, but here you can see it because even though you have a primary carbocation, it's bound to oxygen. So I can do resonance. So if I put a plus charge here and I got an OH here, I can stabilize it through resonance and put a double bond there like that.
So what would happen if you had like two peaks at the same level? How would you determine, like, if, okay, so we're looking at base peaks and then most abundant. What if you had two peaks at the same level? How would you determine which one is the base peak?
That's really rare that will happen. But if it happened, that's a good question. If it happened, you would just have to assign one, right? And if they're both at the same abundance, then you just assign one or the other as the base peak.
Okay.
Yeah, that's a great question. I've never thought about that. But that's a really good question. It's rare that will happen because you're always going to have one fragment that's going to be more abundant than the rest of them. But if you have two fragments that are in the same relative abundance, then you just assign one.
Okay.
Yeah, great question. Great question. All right. Other questions about this example? So I want to end showing you some different fragmentation patterns. So let me go back to the PowerPoint and we're going to look at that real quick. And yeah, let me just show you the different fragmentation patterns here. Yeah, here. All right, so these are some different cleavage patterns. If you have an alkyl chain like this, normally the cleavage favors the branch points on the chain. So if you have something like this, you can see where now you've broken off, or you cleave the bond here, and it'll give you these two fragments, one of them being the radical and one being a cation. Right. So if you have alkyl chains, there's more than likely you're going to see cleavage at the branch points. If you have an alkene, like so, you'll see cleavage at the allylic sites, right? So this is the allylic carbon, and then there's another carbon bound to it. So you'll see cleavage there. So you get like an allylic cation, and then this methyl radical. And then you have what's really common called alpha cleavage. And that just happens adjacent to functional groups like alcohols, amines, and ketones, right? So you have, and we're going to work through some of these on Friday. So you have alcohol here, you can cleave on either side of it. An amine here, you can cleave on either side of it. And then the ketone here, where you can cleave on either side of it. So don't worry about writing this in, because there's a bunch of examples on the handout that we're going to work through. And then if you have an alcohol present, you can also get dehydration, where you lose water and you form an alkene, and you look for a peak at 18 grams per mole, which corresponds to the molecular weight of water. All right. So let me go back. So if you look at something like this, is something that we've done before, right? This is an allylic bromination reaction. And you can see the molecular weight of the starting alkene is 112. We do allylic bromination, and that molecular weight goes up to 190 because of the addition of bromine. And then so we look here, we can have allylic cleavage or cleavage at a branch site. So here you can see the cleavage happening at the branch, and these are my two fragments, or cleavage happening at the allylic site, and then these are my two fragments. Are y'all following? So you look, when you have a molecule, you're looking for these fragmentation patterns, and there are others, but that's just a sampling of what's possible. But you look for these fragmentation patterns where you can chop this molecule up into pieces, and then those pieces get detected, and then molecular weights are going to be detected by a mass spectrometer. All right, so I want to, let's see how much time I got left. So let's run through this real quick. So you got, and this is just a way to think about, the application of this. So you have a patient that dies. It's believed that the patient has been poisoned by his wife. You got crime scene investigators. They think the patient has been exposed to dioxin. So there's the first clue. Okay, if this guy had dioxin in his blood, we should be able to find it, because we know if you think it's dioxin, then you have an idea of what to look for in the mass spec. So if you know the structure of dioxin and the molecular weight, you have an idea of what to look for. So dioxin is the second deadliest poison on Earth, lethal dose of 5 milligrams per kilogram of body weight. The first, believe it or not, is, anybody know that? What the deadliest poison on Earth is? Botox, believe it or not. That's why when people inject it at super, super low concentrations, obviously the dose has to be really low. It causes inflammation. So you inject it into your lips, you inject it into the wrinkles under your eyes, all this stuff. It's going to cause inflammation and make that area look fuller, which I think is, well, not mine. That's my personal opinion. I think it's crazy. But anyway, so let's look at, this is dioxin, has a molecular weight of 324 grams per mole, about 210 different isomers that exist or in this family of compounds, not isomers, but different compounds with a similar backbone. This is the most toxic. It's a carcinogen. It can cause liver damage, death, genetic defects. And this was the major component of Agent Orange in the Vietnam War. I don't know if y'all, well, everybody here is taking history, so you should know about the Vietnam War. But this was a chemical agent that was sprayed during different military operations. They would spray it, as a chemical weapon against the Vietnamese soldiers that they were fighting. But what they didn't realize, or maybe they did, was that prolonged exposure actually causes cancer. It actually causes leukemia. I have a cousin. He's had leukemia now, I think, for 18 years. He was exposed to Agent Orange in Vietnam, and he's still battling that right now. But anyway, what are they looking for in the mass spectrum? If they take a blood sample or a urine sample and bring it to Tuskegee and inject it into our mass spectrometer, what are they going to be looking for if they believe that this person has been exposed to dioxin? How do we know if the wife is going to jail or not?
Is it the chlorine that we found in the blood?
Okay, that's one thing that they could find, but isn't that something more prevalent than chlorine? What if they found something in the blood that has a molecular weight of 324 grams per mole? Wouldn't that be at least a clue that it could be dioxin?
Yeah.
Yeah.
Mhm.
So that would be the parent peak. Is that right? In the spectrum. So if they took a blood sample and they found a parent peak at 324 grams per mole, or they found any peak at 324 grams per mole, it will at least be worth looking into to find out and confirm what that compound is. Go ahead, Cornetta.
So when they're looking for the whole compound, not fragments of the compound.
Well, they're looking for both. They're looking for the whole compound. That has to show up as the parent, but then they're also looking for the fragments as well.
Okay.
So here's the mass
I have a
spec of the
question.
blood sample. Is she going to jail or not?
Yes, she is.
She
She
going
going
to
to
jail. They're about to put them bracelets on. So let's look at what the spectrum looks like.
Dr. Russell,
Yes.
I have a question.
Go ahead.
I know you said they would use the mass spec as like a confirmation. So
Right,
what other like type of test would they do before they do
Well,
mass
well, depending on what they're looking for, like something like this with dioxin, they could actually try to extract from that compound from the blood, and then they can do an NMR. Because if you look at dioxin, you can do a proton NMR. You should have one signal for 4 protons. You see that? There's a hydrogen here, one here, one here, and one here. And because it's symmetrical, you should see one signal. You could also do a carbon NMR. And the symmetry is going to give it away, but you'll have a carbon signal here. You'll have at least three carbon signals. Here with the carbon that's bound to oxygen, and then this carbon and this carbon. But because it's symmetrical on both sides, you should only see 3 signals. Freaking fax machine is ringing. All right. So did that answer your question? Yeah, because there again, the mass spec will tell you if that molecular weight is present, but then you can go in and potentially try and extract out the compounds, especially if you're doing a LCMS, liquid chromatography. You can collect fractions, so that wherever that peak at 324 shows up on the spectrum, you could potentially collect that fraction and do further tests like NMR or infrared. All All right. So this is the mass spectrum. And let's look at the fragments. So this is the main compound, the parent 324. And then you have the loss of a chlorine, which is a possible fragmentation pattern for this compound. That's 289. You lost 2 chlorines, it's 254, 219, 184, and then 177 and 147. And you can see all of those peaks here. And the 35 is the chlorine itself. Right. So that's just an example of how you can use this in practice. So on Friday, we're going to work through the problems in that handout, the last set of problems, mass spec problems on Friday. And we're just going, and we'll take the exam again Friday. I'll post it after class, and you'll have until Sunday to finish it. So with that being said, I'm gonna stop recording and sharing.